Okay, welcome back once again to the tutorial about the chemical applications of group theory. And this is the 8th video in this series. We have been discussing about the application of group theory in spectroscopy. In the last video, we had discussed about the selection rule in electron spectroscopy in terms of group theory. Okay, last we had discussed that two selection rules, the orbital selection rule and spin selection rule. Okay, according to spin selection rule, we have studied that only those transition with no change in spin are allowed. Okay, that is transition from singlet to singlet is allowed. Triplet to triplet is allowed. But singlet to triplet is forbidden. That is, a change in spin is not allowed in electronic transition. And in this video, we are going to discuss about the third selection rule, that is Laporte selection rule. Okay, Laporte selection rule is actually applicable only for center of symmetric molecule. That is, molecules having a center of inversion I. For example, molecules like trans 1,2-dichloroethene, and we know that these molecules have a center of symmetry here. We can draw a line from this chlorine and extend to the other chlorine. It has a center of symmetry. Similarly, from this hydrogen to this hydrogen. Okay, and only this type of molecule the Laporte selection rule is applicable. And all those molecules, that is molecules containing the center of inversion, the irreducible representation, that is IRs, have either G or U subscript. Okay, that is, they are denoted as A2G or B2U, like that. There is a subscript G or U. Okay, and G, we know that it is symmetric with respect to I. That is, if the character of I is equal to +1, then we are using the subscript G. Okay, and G is actually means great, and that it means even or symmetric. Okay, and the subscript U represent anti-symmetric with respect to I. That is, character of I is equal to -1. That means it is anti-symmetric with respect to I. And this U is actually means ungrade in Latin. That means it is uneven. Okay, and then the transition moment integral would be, we know that P is equal to integral -infinity to +infinity psi I mu psi f d tau. Mu is dipole moment operator because electronic transition is an electric dipole transition. And this mu can be resolved into three components, x, y, z direction, and their operator is actually the x, y, z coordinate itself. Okay, so integral -infinity to +infinity psi I x psi f d tau, or psi I y psi f d tau, or psi I z psi f d tau. Okay, that we know already. And for transition to be probable, listen, for transition to be probable, this integral should be not equal to 0. And for that, the direct product of psi I mu psi f should be totally symmetric, and in this case, totally symmetric representation is A1G, because here there is a center of symmetry or a center of inversion. Therefore, the totally symmetric representation is represented as A1G, not simply A1, it is A1G. Okay, that is, psi I x psi f should be A1G, or psi I y psi f is equal to A1G, or psi I z psi f is equal to A1G. Any of this direct product must be A1G, then only the integral not equal to 0 and the transition become probable. Okay, and now, and we know that for center of symmetric molecules, the symmetry of XYZ is always U, or XYZ transforms as U's, because during center of inversion I, X changes its sign, because the coordinate X means a point from this one, it changes to this direction. So X become minus X. So character is minus 1. When character of I is equal to minus 1, then we are using the subscript U. And similar in the case of Y, during the operation of inversion center or I, Y become minus Y, character will be minus 1. And similar in the case of Z, become minus Z, therefore character will be minus 1. So the symmetries of X, Y, Z is always U. This already we had studied. Symmetries of X, Y, Z is always U in the case of centrosymmetric molecule. But we know the symmetry of X square, Y square, XZ, YZ, in all this case the symmetry is G, because the character will be 1. Minus 1 into minus 1 will be 1. Okay, that we already know. So the characters of X, Y, Z or symmetries of X, Y, Z is a U representation. Okay, and now though we know that the direct product relationship is G into G is equal to G, and U into U also equal to G. But G into U or U into G, it is equal to U. That is direct product of two same symmetry is always G. U into U, G into G is U. But different symmetry is U. Okay, that keep in mind. Then hence to get the A1G for the direct product, the psi I, X, Y or Z, psi F, the direct product of psi I and psi F must be U. That is, we know that the X, Y, Z, X, Y or Z is U. Okay, and to get the, we want this integral, that is integral psi I, X, Y, Z, X, Y or Z, psi F, the direct product of these three should be A1G. Okay, and this term or the symmetry of X, Y or Z is U. Okay, we learned here. So to get A1G, the direct product of psi I and psi F should be U. Then only U into U should be equal to G. Okay, we know that U into U is G, but G into U is U. Okay, because listen once more, that is, we want to get this direct product, that is psi I, X, Y or Z, psi F to be A1G. We want to get that, then only the integral will be non-zero. And we know that this symmetry of X, Y or Z is U. Okay, and direct product of U into U is G, but G into U is U. We want to get G. Okay, then the direct product of psi I and psi F should be which one? U. Then only here it is U. So direct product of psi I and psi F should be U. Then only U into U is equal to G. Understood? Okay, that is psi I, U psi F should be equal to A1G. X, Y, Z is equal to U. Then to get A1G, psi I into psi F, direct product of psi I and psi F should be U. Then only U into U is equal to G. And to get psi I into psi F is equal to U, okay, then psi, one of the thing, either psi I or psi F should be G and other should be U, because we should get U only in the case of U into G is equal to U or G into U is equal to U. Okay, that means psi and I and psi F should have different symmetry. Okay, that is we are saying here, for that psi I and psi F, one has to be U and the other has to be G. I am saying one more. That is, we want to get psi I symmetry of x by z, that is u, into psi f should be equal to g, a1g or g. Then to get g, the psi I into psi f should be u. Then only u into u is equal to g. And to get psi I into psi f is equal to u, the psi I and psi f should have different symmetry. That is, one of them should be g and other should be u. Or one of them should be u and other would be g. Okay, that is psi I and psi f, one has to be u and the other has to be g. Then only u into g or g into u is equal to u and u into u is equal to g. Okay, can you follow me? Okay, that is psi I and psi f, that is initial state and final state should have opposite symmetry. That is, if psi I is g, then psi f should be u. Or when psi I is u, then psi f should be g. Okay, thus for transition to be allowed, the initial and final state must have different symmetry or different parity. Symmetry, or otherwise we say it is parity. Okay, so Laporte selection rule can be stated as, for center of symmetric molecules, the transition between states of same parity are forbidden. For Laporte selection rule is simple, very simple. It states that, okay, for centrosymmetric molecule, electronic transition between states of same symmetry or same parity are forbidden. That is, G into G transition is forbidden. U into U transition is forbidden. Only G into U, G to U or U to G transitions are allowed. Okay, very simple. That is a Laporte selection rule. That is, transition from one level to the higher level, this level, the initial and final state should have different parity. That is, one of them should be U and the other should be G. Okay, that is, U to G or G to U transitions are allowed. G to G, U to U transitions are forbidden, and that is the reason. Okay, and before yes, okay, we can illustrate this Laporte selection rule taking benzene molecule as example. Benzene belongs to D6H point group, and the pi molecular orbitals of benzene are A2U, a non-degenerate level, and E1G, a doubly degenerate level, and E2U, a doubly degenerate level. That is, one level is, that is A2U, another two level E1G, E1G, and another also two level, that is E2U, E2U, and the last one is also A2U. Okay. So the ground state configuration is, there are 6 pi electrons occupied like this. Okay, so it is A2U2, E1G2, E1G2. Okay, since all the electrons are paired, the symmetry would be A1. Okay, we already discussed that if an orbital is fully occupied or it is paired, then their direct product will be a totally symmetric representation. It is A1, or we can say A1G. Okay, clear? That is, the picture is like this. It is A1U, it is E1G, it is also E1G, it is actually it is E2U, it is also E2U, like that. Okay, and these 3 levels are occupied, A1U2, E1G2, E1G2. Okay, then the lowest energy transition is from E1G to E2U. That is, our level is like this. That is, it is A2U, it is E1G, A2U2, E1G2, E1G2, it is A2U, it is also E2U. So transition, lowest energy transition is from HOMO to LUMO, that is this E1G level to the E2U level. So we are considering E1G2 to E2U transition. The excited state configuration would be A2U2, E1G2, E1G1 and E2U1. The symmetry of the excited state, this is doubly occupied, so it is A1G. It is also doubly occupied, it is A1G. So symmetry is decided by the direct product of this two level, that is E1G into E1G. Okay, no, it is not E1G. Yes, okay, it is not E1G, it is E2U, E1G, E2U. Okay, so E1G into E2U, E1G into E2U. So the symmetry of the excited state is decided by, because these two are A1G representation, because they are doubly occupied. Singly occupied levels are E1G and E2U. So the symmetry of the excited state is decided by the direct product of these two, that is E1G, E2U. And that direct product on calculation, I am not explaining much more. The result is, or that is direct product of E1G, E2U. E1G into E2U is equal to B1U, B2U, E1U. Okay, you can calculate using D6S point group, you can verify this. Okay, so the lowest excited state has two, this is the excited state. Okay, so the lowest excited state has two non-degenerate states, that is B1U and B2U, and a doubly degenerate state E1U. Can you follow me? That is, the symmetry of the excited state is the direct product of all these things. But these direct product are actually A1G. So the symmetry of the excited state is decided by the direct product these two, that is E1G, E2U. And the direct product of E1G, E2U, we get three levels. So the lowest excited state has three, not actually three, it is actually four. That is, one is a non-degenerate B1U level, another also non-degenerate B2U level, another one is a doubly degenerate E1U level. So now we have to consider three transitions. We have to consider three transitions, that is A1G to B1U. The lowest level, ground level is always A1G. Excite level, there are three excited level, B1U, B2U, A1U. So there we have to consider three transition, A1G to B1U, A1G to B2U, A1G to E1U. Ground state is always A1G. Ground state is A1G, we have calculated, because all the levels are fully occupied A1G. Excited level, there are T level, B1U, B2U, E1U. And all these are GU transition, A1G to B1U, G to U. Here also A1G to B2U, G to U. Here also A1G to E1U, G to U transition. So according to Laporte selection rule, we have studied that only those transitions with change in parity or change in symmetry are allowed. And all these are G to U transition, all these transitions are Laporte allowed by Laporte rule. But according to orbital selection rule, Laporte rule, these all transitions are allowed, no problem. But according to orbital selection rule, the direct product of psi I into psi f should have same symmetry as any of the XYZ. That is orbital selection rule. That is the first selection rule. Direct product of psi I into psi f should have the symmetry of X, Y or Z. Okay. And from D6S point group, it is seen that B1U and B2U do not belongs to any of the coordinates X, Y, Z. Okay. One more, you listen one more. That is, according to orbital selection rule, psi I, X, Y, Z, psi f should be A1G. That is our selection rule. Okay. Then here psi 1 is equal to psi 1, we already get, it is A1G representation. A1G. Okay. Psi 1 is A1G. Then psi f is here, we get three level, that is B1U, B2U, E1U. It is not A1G. So the symmetry of X, Y or Z should have same as that of psi f. Okay. Same as that of psi f is B1U or B2U or E1U. But XYZ coordinate does not belongs to B1U and B2U. So according to orbital selection rule, transition from A1G to B1U and B2U is not allowed because their symmetry are not belongs to XYZ coordinate. But E1U belongs to XY coordinate. I am not explaining this much. You can check it by taking the D6H character table. Okay, so the only allowed transition in benzene is A1G to E1U transition. Okay, can you follow me? There are three excited states: B1U, B2U, and E1U. Okay, and there are three transition possible: A1G to B1U, A1G to B1U, A1G to B2U, A1G to E1U. Okay, all are symmetry allowed or Laporte allowed, but orbital selection rule, by checking the orbital selection rule, we can see that these two transitions are not allowed because their symmetry not belongs to XYZ coordinate. Only E1U has coordinate, XY coordinate belongs to E1U. Therefore, A1G to E2U transition is the only allowed transition. Sorry, A1G to E1U transition is the only allowed transition in benzene. Okay. And the last point is this one. The Laporte rule forbid DD transition in octahedral metal complexes. Okay. Because in octahedral complexes, the transition is from T2G to EG. You remember in the lower class you have studied that the DD transition is actually from T2G to EG. This transition is not allowed because it is G to G transition. Okay, this transition is not allowed because it is G to G transition. According to Laporte rule, G to G transition is forbidden. That is why DD transition is a forbidden transition in metal complexes. But even though DD transition takes place, that we know most of the octahedral metal complexes are colored, and that is actually due to the we have studied in the last video, that is it is due to the violation in selection rule. It is actually due to the vibrational coupling, vibronic transition that we have studied in the last some of the videos. Okay, and this is the end of this class. Okay, watch this video carefully and read the textbook very well. Thank you.